Okay. Let's see. So let's try to do problem 3.49. Okay, so let me just grab hold of the problem statement. So I'm gonna quickly stop sharing. I'm gonna grab the problem statement. Hmm. So this is the problem. So the schematic of the problem also you must be able to draw. So two tanks are connected as shown in the figure. Okay, let's draw the figure. So we have one tank and another tank, and they are connected by a pipeline, and there is a small valve in the middle. Okay, there is a small valve in the middle. So this is tank A and this is tank B, and they both contain water. They both contain water. Tank A is at, so the condition over here is 200 kilopascal, and the specific volume is given as 0.5 meter cube per kg, and the absolute volume, so the total volume is 1 meter cube. All right. Tank B, this contains water at a pressure of 0.5 megapascal at a temperature of 400 degrees Celsius, and it contains a mass of 3.5 kilogram. The valve is now opened and the two come to a uniform state. So the question is, find this final specific volume. Okay. So the question is rather simple. The question is simply asking you that question simply says find the final specific volume. How do you go about it? Okay, let's look at the problem uh, from the end state. So you need to find the final specific volume. So final specific volume. So what will be required in order to find out the final specific volume? You need to know the total mass finally, and you need to know the total volume finally. If you know the total mass and total volume, then you will be in a position to find out the final specific volume. So, do we know the total mass of the system? Over here, we only have the specific volume and the total volume. Okay, so the mass in system A will be equal to the total volume divided by the specific volume. So, what is this going to be? 1 over 0.5, and this is going to be 2. So, 2 kilogram. So chamber A or tank A, it contains 2 kilogram of water, whereas it is directly given that chamber B contains 3.5 kg of water. So the total mass is going to be, when the valve is open, the total mass in the entire system is going to be Ma plus Mb, and that is going to be 2 plus 3.5, which is going to be 5.5 kilogram. Now what about the total volume? So the volume of tank A is directly given as 1 meter cube. What about tank B? I must know the total volume of tank B. I only have the mass. So in order to find out the total volume, so you can simply write MB is equal to VB over small v. But the problem is I do not have directly the value for this specific volume in tank B. But what I do have are two independent parameters which have been given to me. I have two independent parameters with the help of which I can determine V. Once I can determine V, I can plug it in over here and find out the total volume VB. So the problem is just to determine the specific volume small v. So let us first go to ES. So we are in ES now, and let's see, let's get this. So VB, the specific volume of B, and this is going to be volume steam P equal to 400, P equal to 500. And I can also directly write MB is equal to 3.5, and I can write VB equal to MB times VB. I've just used this particular equation, I've written it down. So I will directly use ES and get the total volume. Total volume comes out to be 2.161 meter cubed. Okay. So let's just write down. So VB is 0.6173. So we get VB is 0.6173 meter cube per kg, and capital VB as 2.161 meter cubed. So we have total mass, and the total volume will be equal to VA plus VB, which is 1 plus 2.161, which is 3.161 meter cube. So the final specific volume is equal to 3.161 over 5.5. And so what is this? So I can use the engineering equations all over here as well. V final is equal to I can say VB plus 1 divided by MB plus 2. VF comes out to be 0.5746. I've just used it as a calculator. Okay? Don't be confused what I'm doing over here. 0.5746 meter cube per kg. Okay. So first of all, is the logic of the problem clear?
Yes, sir.
Yes, sir.
So now let us do the tedious part. Let us try to fetch the values with the help of the actual steam tables. So let me go to Sontag. So what do we need? So at 0.5 megapascal, 400 degrees Celsius. Someone wants to say something?
Sir, here we are given for the B part, P is equals to 0.5 and T is equals to 400. But sir, we read earlier that by knowing only P and T, we cannot get the complete information.
Yeah, so by only specifying P and T, you cannot get the complete information inside the saturated dome.
So yes, sir. That's why I'm asking how we come to know that this is not under saturated region.
Yeah, so the problem if they say something like this, and if the problem is not ill-posed, there are two ways of going about it. First of all, they have given in the problem. So you know that the problem setter will not give you such kinds of absurd initial conditions where the initial state itself is not known. So I know that this is going to be in superheated vapor. But you don't need to take my word for it. You don't need to take my word for it. So what we will do is at 0.5 megapascal, we will simply first query what the T saturation should be. Meaning, in my mind's eye, I will do the following. So this is P, this is V, this entire line is going to be 0.5 megapascal. So first, my task is to find out what this temperature is. So Tsat at 0.5 megapascal. Okay, so let's see what Tsat at 0.5 megapascal is. No, what you asked is very pertinent in actual engineering. No one will say. So Tsat 1 is equal to temperature, team.
Sir, hello, sir.
Yeah.
Sir, can I directly ask for the quality?
Yeah, you can also query the quality. You can also directly query. I mean, okay, let's write down both the commands. So x1 equal to quality steam, T equal to 500, T equal to 400. You can also do that. So we get x1 equal to 100. Very good. And Tsat 1 is 151.8. So directly the computer tells that the quality is 100 and this temperature is 151 point something degrees Celsius. And the actual temperature is 400 degrees Celsius. So the 400 degrees Celsius isotherm will be this 400 degrees Celsius. So obviously the intersection of the 400 degrees Celsius isotherm and the isobar P equal to 0.5 megapascal lies in the superheated vapor region. And the region, not the region, the reason why I did this is because when you look at the table, obviously you cannot do this step in a table. You will not be able to do this particular step using a table. I mean, you will go all around the place. So you simply get what the saturation temperature is, meaning you simply query what this temperature is, this isotherm is. Okay, so it is basically saturation temperature corresponding to 0.5 megapascal. So that we can easily get using a table. So we go to superheated vapor 500 kilopascal. You have superheated water vapor 500 kilopascal. In the bracket it says 151.86. So 151.86 is the saturation temperature which corresponds to a pressure of 500 kilopascal. So obviously the temperature presently is much higher than the saturation temperature. And like I had said in the very beginning of this course, when the temperature is larger than the saturation temperature, the system is in superheated condition. So at 500 kilopascal and 400 degrees Celsius, the specific volume is 0.61728. You seeing this? Let me take a screenshot. Okay, so at 500 kilopascal, 400 degrees Celsius, the saturated, I mean, not the saturated, the specific volume is 0.61728, and we had obtained from the computer 0.6173. Not bad. Okay, so now you would have obtained this step. You would have obtained this step, and then everything else just follows from the same chain of logic. Okay. This is table 3.2.1, superheated vapor. Is that clear to everyone?
Yes, sir.
All right, let's do another problem.
In the last problem, I have a doubt.
Last problem meaning the one we just solved.
Yes, sir.
And what is the doubt?
Sir, why we directly added the two volumes in the final state?
Because when the valve is open,
Sir, pressure and temperatures will change finally, and
yeah, so for pressure and temperature, in order to figure out the actual state, we need to use the first law, which we have not yet studied.
sir, it will
Yeah.
not influence the final volume,
No,
and
how
we
can
can.
it? So look. Thermodynamics is one thing and physical transport of mass is another thing. No mass can escape the entirety of the volume A and B. Whatever the mass is, whenever it gets redistributed, obviously mass is not going to vanish. That is why we can write down the total mass with confidence. And also, if you neglect the volume of the pipeline, okay, you have to simply neglect this volume, this pipeline volume. So the total volume finally will also be the total volume will be just comprised of volume of A plus volume of B. After opening the valve, whatever mass is there, it will get redistributed. It will not literally change the total amount. So in this case, I mean, we've done it implicitly, but this is the control system. Okay, this is the control volume rather. Control volume. Okay. No mass is entering or leaving into the control volume. Neither is the volume not changing. So these are rigid tanks. So whenever you say a tank, the volume of the tank is not going to change. Okay, that is why we could do whatever we have done. Does that make sense to you?
Yes, sir.
So now we're going to do problems 3.60. Okay, so we're going to do problem 3.60. Let me just stop sharing the screen real quick. And let me take there are no hotkeys. I would have really liked if there would have been hotkeys for everything, but okay, so this is the question. A sealed rigid vessel of 2 meter cube contains a saturated mixture of liquid and vapor R134A at 10 degrees Celsius. If it is heated to 50 degrees Celsius, the liquid phase disappears. Find the pressure at 50 degrees Celsius and the initial mass of the liquid. So let's do it. Let's draw. So we have something like this, and that's it. I mean, this is the entire schematic. So this total volume is 2 meter cube, and it contains R134A, which is a very popular refrigerant. You might have seen this. This is widely used in car air conditioners, in vehicular air conditioners, and a few, like maybe 5 to 6 years ago, it used to be used in household air conditioners as well. I think it was banned all over the world because of its greenhouse impact, greenhouse potential, but it's still used in Japan and India. All right, so it contains this. So now when you heat this, so it is heated. So once you heat it to 50 degrees Celsius, the liquid phase it disappears. Okay. And so we simply need to find out the final pressure at 50 degrees Celsius and the initial mass of the liquid. So let's draw the schematic, what's going on. So the initial condition is somewhere over here. This is the PV diagram. It's gonna be somewhere over here. So this is one isotherm. This is the 10 degrees Celsius isotherm. This is 10 degrees Celsius isotherm. It is given that the initial volume is 2 meter cubed. And when it is heated, we see that the liquid phase disappears at 50 degrees Celsius. So what should we do? We have to first draw the 50 degrees Celsius isotherm, and the 50 degree, the intersection of this vertical line, this is state 1, this is state 2. So the intersection of the vertical line with the 50 degrees Celsius isotherm defines completely what state 2 is going to be. So quick question, why is 1 to 2 process vertical line?
So the volume of the control volume is constant.
So the answer is the mass and volume of the control volume is fixed. The control volume is simply going to be this particular thing. Control volume is going to be this particular thing, right? Because no mass is going to leave or the volume is not going to change, the process on the PV diagram will be a vertical straight line. Now we don't know exactly where point 1 is. Okay, we could have started over here as well. Who knows? I could have very well started over here. But the final state is at 50 degrees Celsius, and at 50 degrees Celsius the liquid phase disappears. Now if this was to be the starting point, 1 prime, I would end up over here. So quick question, why is 1 prime to 2 not the process?
So the liquid phase disappears.
The liquid phase disappears.
Someone else.
The
Not
liquid
you
phase
guys.
disappears.
You guys are, oh, someone is Aniruddha, he knows the answer. No, come on, you can lower your hand. I know you know the answer. Let's go to someone.
Sir, can I speak?
Bhanu Pratap. Okay, Bhanu Pratap, you can answer.
Yes, sir, because it is given at 50 degrees Celsius, the liquid should disappear. That means it should be transferred into a superheated steam.
Okay, so look, let's go by what you just mentioned. I can also start over here, 1 double prime, and I can go to this state. This is 2 double prime. Quick question, why is 1 double prime, 2 double prime not process?
Because, sir, here before 50 degrees Celsius, here we can reach a point where it will change into a superheated gas.
Okay, very good. So is it clear to everyone? Not the usual guys. I know this is very easy, but this should be clear to everyone. Okay, let me just put it this way. Whatever we have discussed should be very, very obvious to everyone, because otherwise, if you're not getting this naturally, it will be difficult for you to attempt problems later on. So state 2 is basically R134A at 50 degrees Celsius x equal to 1. And state 1, the only information we have is total volume equal to 2 meter cubed and temperature is equal to 10 degrees Celsius. The question is find the pressure at 50 degrees Celsius and the initial mass of liquid. So, quick question. What is the pressure at 50 degrees Celsius? How would you find out the pressure at 50 degrees Celsius?
So
So
pressure
we will
will be set for
It will be
corresponding
Psat at
T is equals to 50.
50 degrees Celsius. Very good. So, that would take care of the first part of the problem. There itself you have obtained 2 marks. Okay. Typically, you would be awarded 2 marks for your effort. Second question is find the initial mass of the liquid. How do you find out the initial mass of the liquid?
specific
Sir, we
volume
can
into
find the
the volume of the container.
Well, it's very simple. You don't find out the initial mass of the liquid. Why would you want to do that? You know that the initial mass and the final mass is going to be the same. So asking this is also tantamount to what is the final mass of the system, or what is the literally mass of the system. So at this point, so what the strategy should be is find specific volume at state 2. Okay, you will find the specific volume at state 2, and you know that regardless of whether the system is at state 1 or state 2, so we know what V2 would be. We know what the total volume at state point 2 would be. What will be the total volume? What will be the total volume?
2
2
meters.
meters.
It will be still 2 meter cube. So once you know the specific volume at state 2 and the total volume, how will I find out the mass? It will be total volume over the specific volume. That's it. We will use this formula to fetch total mass. I will quickly do it on ES and show it to you. So let's get rid of all this. So I will not define everything as arrays because I would like to eventually plot it. We would be very much benefited if we are able to plot that thing as well. Okay, so let's do it. So T1 is 10 degrees Celsius. V total is 2 meter cube. T2 is 50 degrees Celsius. P2 is pressure of R134A at T equal to T2 and X equal to 1. Actually, it doesn't matter what value of X you use because when X varies from 0 to 1, the saturation pressure will remain the same for a given temperature. I've told this many times. Okay, then I will say V2 is equal to volume, and then I will simply copy paste this because the conditions are identical. Okay, then I will say that this is also going to be equal to V1. This is also going to be V1 is also going to be equal to V2. Is it clear why V1 is going to be equal to V2? Guys?
Yes.
Yes, sir.
It's literally on the
Yes, sir.
vertical line. So V1 and V2 are equal. So just when we do this, okay, let's just write the total mass. Mass total is equal to V total divided by V1 or V2, doesn't matter. Same thing. It's literally the same thing. So we need P1 as well. So P1 will be pressure R134A T equal to T1. And now what should I specify? In order to completely specify what point 1 should be, what is the other thing? I have specified temperature. What should be the other property?
Sir,
Quality.
V2.
It should be the specific volume. So I can add V equal to V1 just to maintain sanctity. Okay. Because over here I have evaluated what V1 is. So I can use V equal to V. Actually, in ES, it doesn't matter what sequence you enter the commands, it will eventually do them all at once. But over here, logically, we have evaluated what V1 should be. So over here, we are using that same value. I could have very well written over here V2, no problem. You get the point, right? Could have very well
Yes, sir.
done that. So let's Run this. The total mass is, that's a lot of mass. Have you made a mistake somewhere? Who knows? 132.6 kilogram. Okay, that's a lot
Sir,
of
we
mass.
also got the same mass.
Oh, okay.
Yes, sir. Yes, sir.
So you're solving along. That I'm very happy to learn that. Please.
Yes, sir. Doing in ES.
Oh,
Sir,
but
I'm solving using that table.
yes. Okay. Nice. So good. We have all sorts of solvers. So we will go to plot property. So first we'll do the property plot R134A. Where is R134A? It's over here. We will go to TV or PV plot. We go to PV plot. We don't want to include all these lines. Get rid of those. But we do want to plot 10 degrees Celsius isotherm and 50 degrees Celsius isotherm. Okay. So when I click on OK, I get the plot. When I click on OK, I do get the plot. Now on this plot, what I need to do is I need to overlay the points. So I go to plots, I go to overlay plot. On the x-axis, I have the specific volume. On the y-axis, I will choose temperature. I will click on OK, and everything is. Oh no, it was not temperature. It was supposed to be pressure. Okay, okay, okay. How to get rid of this plot? But anyway, so we go to plot, overlay plot. On the x-axis, we have the volume. On the y-axis, we have the pressure. I don't know why. Okay, so this is the process. Okay, this is the process. This is point 1, this is point 2. Okay, is it clear to everyone?
So using the table,
How will we able to plot a point in this table?
How will you plot the?
Any if you want to plot any point
You
in
must declare
this,
it as an array. That is the only way to do it. You must declare it as an array, and you must then overlay those array points. So it will take the array points and it will just plot it all over the place. You just look at this now. You have the example code in front of you.
Sir.
Yeah.
Sir, after
Yes.
the class, can you share your that video links that you made on ES?
Yeah, I'll do that. I have to make a playlist out of it. It's so many videos in my channel. There's so much junk in my channel that someone needs to sit down and actually make a playlist out of it. I will give you the link. You can try to make the playlist out of it. You just sort it by date. You will get all the videos.
Okay, sir.
That will help me also.
So can you please solve using the table once I'm getting some incorrect answer?
Yeah. So we'll now go to table. So in table R134A, so what was the thing that we did? So at 50 degrees Celsius, we need x equal to 1. So R134A, we need the specific volume, 50 degrees Celsius, x equal to 1. So let's go to the table. So we're in the table. So we have to go to R134A. So this is
So I have
compressibility.
put in chat that table screenshot.
ठीक है, I mean, we'll seek it. We'll see how in the current situation you would scroll through a bunch of pages. R12, we are now in R12, R22. R22 is used in most household refrigerators nowadays. R22, R134A. We're in R134A. So in R134A, what was the, so 50 degrees Celsius. So this is 50 degrees Celsius. So at 50 degrees Celsius, the saturation pressure is 1318.1. So 1319, close enough. 1318.1, 1319. Okay, so at 50 degrees Celsius, the specific volume of vapor is 0.01512. 0.01508. Close enough. Who, I mean, not who, but is it clear to whoever asked?
Yes, sir. So I was looking at the wrong table only.
So this, don't do that error.
I was looking at the water table. That's why I put
Yeah,
the reference.
I sort of figured it out that you were looking at the wrong table. But don't do that. Huh? Those kind of mistakes are what you may say unpardonable. Will bring you great anguish. Just mark it over here. So R134A and 50 degrees Celsius, saturation pressure is this, specific volume is this, and the rest you know how to do it. Okay, the rest you know how to do it. So by now you should be able to comfortably fetch values from the table. Okay, so as a small reading task for everyone, please, okay, no reading task, but you just solve problems, solve as many problems as possible. So there are many more problems in this. I mean, obviously they look complicated. So the problems are not complicated, but they simply look menacing. So I'm giving you a bunch of problems to solve. You don't need to do it right now, but you eventually need to do it in your life. So they are so-called difficult problems. So I'm going to write it down over here. So you should do problem 3.94. I mean, I don't want to write this 3 point every time. So this is Sontag 6th edition. Sontag 6th edition, chapter 3. So all the 3 points are assumed to be there. So you do 94, 97, 99, 101, then 113. In fact, you should also do 105. In fact, 105 maybe I'll do it. I'll do it after a short break. I will do this. Then 111 also. There's this, so 6 problems. I will do this after the break. So just take a 5-minute break. I'll be back. And then you can start attempting 100. So let's do 105. Am I audible or gone wrong?
You are audible, sir.
Not shared
Yes,
any
sir.
screen.
Yes, sir.
So screen should be visible. 105.
So only the writing app is.
Yeah, wonderful. This is the problem. You must first conceptualize the problem before going to like fetch any property or anything of that kind. Okay. So it says we have a diagram as well. The diagram is sort of straightforward. You have a cylinder like this. You have a piston like this. The chamber then has a spring like this. And this initially, I mean, not initially, this contains water. This contains water. So it is given that state 1, it contains water at 105 degrees Celsius, 0.85 quality. So the quality is also reported in percentage. Instead of reporting it as a fraction, it's also reported as a percentage. So we will just convert the percentage into a fraction. And the initial volume is 1 liter. Okay. So the initial volume is 1 liter. The system is heated, causing the piston to rise and encounter a linear spring. Okay. So in the problem, the spring is actually not initially engaged. The spring is not initially engaged. So let's see how we will determine state 2. Okay, let me also draw the PV diagram. In the PV diagram, so initial quality is 0.85. So this is x equal to 0.85. So maybe the point is somewhere over here. So this is state 1. So this is P, this is V, this is the isotherm. So this isotherm will be 105 degrees Celsius. Okay, very good. And the system is heated, causing the piston to rise and encounter a linear spring. So what is happening is this piston is rising and this is state 1. So after rising, it will like just touch the linear spring. It has not yet compressed the linear spring. So this is state 2. So what is process 1 to 2? Quick question. What is process 1 to 2?
So isobaric.
Very good. It will be an isobaric process. Okay. So it will cause the piston to rise and encounter at this point the volume is, so for state 2 the volume is 1.5 liter. So whatever the pressure was at this point, let's call it P1, the same will be the pressure at point 2 as well.
Sir, why is it isobaric, sir?
Pardon me?
Sir, why is it isobaric, sir?
Because when the spring has not been in contact with the piston is simply rising up, and the pressure that is acted upon on the fluid is solely because of the weight of the piston and the atmosphere. The weight of the piston and atmosphere is not changing. Does that make sense?
But the spring is exerting some pressure after the.
But this is the point where the spring has just come into contact. Spring has not been compressed at this state. Is it clear? It says, I mean, the next part of the question is the heating continues and the piston compresses the spring. So at just point 2, we have not yet compressed the spring. So the spring has had no effect on state 2 so far. Is that clear?
Yes, sir, I understood.
It is given that the piston diameter is, so this diameter is 150 mm and the spring constant K is what? 100 Newton per mm. This is what we know. So then the next information is the heating continues, so the piston compresses the spring. Okay, very good. So what is the cylinder temperature when the pressure reaches 200 kilopascal? Okay, so this is what the question is. So this is obviously some pressure, maybe let's call it P1. This pressure is P1, and obviously P1 is less than 200 kilopascal. So this is P1. And how will we find P1? P1 will be simply the saturation pressure, which corresponds to a temperature of 105 degrees Celsius. Now what I will do is I will plot P3. So state 3. So P3 is going to be 200 kilopascal. That's it. We don't have any other information. Okay, we don't have any other information. So state 3 will be somewhere on this curve. But so now the question is, what is process 2 to 3 on the PV diagram? How will the process look like?
Straight line, not like an angled line.
So it will be an angled line. So let us not try to justify why it will be an angled line. Okay, so you have the piston like this, and you have the spring like this. So when the spring gets compressed by an amount of x, x is perhaps a very poor choice of variable because x is also quality. So we say some displacement d. Okay, let's say there is a displacement d. There is a compression. So what is the force due to that displacement?
So
So the
KD.
force acting in this direction will be equal to,
Delta P into A.
yeah, but I mean in terms of the spring constant.
K delta
So
P.
KD.
So it will be Kd. And so what is the corresponding pressure? What is the corresponding pressure?
KD
P
upon
due to spring.
R.
So Kd over the area of the piston, right? And the total pressure exerted by the piston and the spring will be pressure without spring plus pressure due to only spring. Why is there a pressure without spring? Because we know that the piston has some mass, otherwise there would be no pressure in the system, right? So it would be pressure due to spring would be equal to whatever this pressure is, whatever this P1 is.
So 120.9.
Okay, so someone has gone ahead and figured out the pressure corresponding to P at 105 degrees Celsius. The saturation pressure at 105 degrees Celsius is
120.9.
120.1 kilopascal. So we now know, thanks to the effort of some students, that this pressure is 120.1 kilopascal. So obviously this pressure without spring would be 120.1 kilopascal, and the pressure due to the presence of the
Sir,
spring,
it's 120.9, I guess.
it doesn't matter. I mean, the values right now, it doesn't matter. We just like to do it symbolically. Okay? Forget about this. But it is what they said it is. So let's just call it P naught. So now the pressure due to spring is K D over area of the piston. Okay, very good. So now how do we sort of make sense of this? So let me just rearrange. So P is equal to P naught plus K D area of piston over area of piston squared. I can do this, right? I can easily do this. Okay. Now this is P naught plus K over area of piston squared. So now DAP becomes equal to delta V. D times AP. So D is the displacement of the spring, or rather the compression of the spring. And area of piston is this cross section area. So this displacement times the area is like the volume swept by the piston due to the compression of the spring. Is that clear what this term is?
Yes, sir.
Yes, sir.
All right. So with that in mind, we can write this down as P naught plus K over AP square times some volume, final volume, minus the volume where the spring is not compressed at all. It's gonna be V minus the volume where the spring is not
1.5.
compressed. Yes.
1.5 into 10 to the power minus.
No. So I mean, let's just call it as V without spring. Okay. This is the volume without any spring. So that is why. So if you look at how the curve varies, so P varies linearly with V with this slope and this intercept. Okay.
Yes, sir.
So that is why it's a linear curve.
Sir, I have a doubt.
Yeah.
Sir, how sure are we that the point 2 is inside the saturated
We
zone?
don't know. We don't know that. I've just drawn it.
Yeah, yes, sir. I mean, I calculated the value and I got the value to be outside the zone.
Yeah. But
So then,
even if it is outside, it will go on the straight line.
okay, yes, sir. Yeah, got it.
When it is outside, it will go on the straight line. Okay. He's correct. We don't know where the point 2 is. It could be here, but wherever it is, if this is point 2, then point 3 will be like this. Okay, so it doesn't matter where you draw this. I mean, of course it matters, but for the schematic, it doesn't matter. Okay, so now you know that it's a straight line with a certain slope. Very good. Is there some other way I can quantify what the final state point 2 will be? Of course I can. From state point 1, I will know not only the pressure. So at state point 1, I know temperature equal to 105, quality equal to 0.85. With the help of these two parameters, I can find out the specific volume at state point 1. With the help of the fact that the total volume is given, I can find out the total mass of liquid in the system. Now at state point 2, and because I know the total volumes, it is 1 liter. At state point 2, I know that the pressure is going to be the same as pressure at 1. So P2 is going to be P1. And I will easily be able to figure out what the specific volume at state point 2 will be, because I now know the total mass in the system. So it will be equal to the total volume at state point 2 divided by the total mass. And the total volume at state point 2 is given as 1.5 liters. So I will know entirely what state point 2 is going to be. Okay. Now, when we go to point 3, you know what pressure, we know what P2 and total volume at 2 is going to be. We know what P2 and total volume at 2 is. We know what the final pressure is going to be. And because we know how to evaluate the slope, we can easily determine what the total volume at point 3 will be. And because we will know what the total volume at point 3 will be, and we know that the total mass of the system, meaning the total amount of steam in the system, is also fixed, we will easily be able to figure out what the specific volume at point 3 will be. At point 3, we would know P3, total volume, specific volume. So we would also completely know what the state point is. Basically, we would know P3 and specific volume at 3. And now once we know what P3 and V3 will be, we can use these properties to find out what the temperature at point 3 will be. Any doubt in how we will go about the problem? Hello?
So, could you explain once like how we are finding the volume at 3? Like using that slope and
We know the, yeah, exactly. It's just a linear line.
okay, so
It's just a line. Nothing sacrosanct about it. It's just straight
yes,
line.
yes, got it.
So the slope, intercept, everything we know. Okay.
Yes, sir.
So now let's literally put the numbers and let's see what we get. So P1, I'll open up. So I only shared my screen. Here we go to EES. Close all this. Get rid of all this. Okay. So in fact, I mean, it's good to do it as an array. So we say pressure, steam, T equal to 105, X equal to 0.85. I mean, actually, X equal to 0.85, it doesn't matter because it is PSAT. So I can use any value of X. But still, just because I will be copy pasting this, so this will be volume and we paste. Okay, we have the volume. So then the V1 is going to be 1 liter. So 1 liter is 10 to the power minus 3, right? So this is the initial volume. In fact, let me, yeah, so this is state point 1. Are we missing something? The total mass. So total mass will be, how do we figure out? It will be the total volume V1 divided by V at 1. Let's just do this. So what do we get? 120.9. Okay, that's the state point 1 is V equal to 1.209 P is equal to 120.9. So they are all standard units, kilopascal, meter cube per kg. Total mass is 0.00308292. Okay, so we have this so far. Now state point 2. Okay, so we'll go to EES once again. We will first of all say that P2 is going to be P1. That much is clear. Then V2 is 1.5 times V1. Okay, because I mean, I'm just not hard coding it. It is just 1.5 times V1. Okay, it is 1.5 liter, nothing else. V2 is 1.5 liters, which is nothing but 1.5 times the initial volume. Okay, I've done nothing fancy. Okay, what else do we know at state point 2? Total mass is, so if V2 is this, I can write V at state point 2 is going to be the total volume at 2 divided by the total mass. So this would give me the specific volume at 2. Okay, so let's run this. So specific volume at 2 is 1.809. So state point 2 is 1.809.
Sir,
Yeah.
so here the unit of volume in the question is in liters, so we first have to convert it in meter cube. No?
I have converted it into meter cube.
Oh yes, sir. Sorry, sir. I didn't saw that.
Yeah. MT is going to be the same. Okay, so now we have the entire second point as well. Okay, the volume 1.5 lit. The volume is 1 lit. Okay, now we need to really be concerned about the unit because state point 3, so P will be equal to 200 kilopascal. And obviously total mass will be also the same. But yeah, so this is only what we have. So now let us try to find out what P at point 3 is, the total volume at point 3. What is it? Volume. Okay, so let's just quickly run the numbers. So P is equal to P naught. So P naught will be this 120.9 kilopascal. You need to write down the units here because otherwise you will mess up. So now K, the unit of K is 100 Newton per mm. So this is 100 Newton per mm divided by the area of the piston squared. So the area of the piston is pi d square by 4. So 150 mm. So pi by 4 into 150 mm squared times V minus like 1.5 liter. So this is liter. So we must make sure that in the end, whatever mumbo jumbo you do to this, you get a kilopascal over here. This is what you need to ensure. Is that clear? Because otherwise you cannot add it to this. Okay. So what is this? 400 over pi. So you get a 150 squared and you get Newton per millimeter, and there's a millimeter square over here, and from here there is a V minus 1.5 and this there is a liter over here. So liter is dm cube, right? 1 liter is decimeter cubed. So decimeter cubed in terms of millimeter, what is it? 100. So it is 100 millimeter cubed. Are you following what is going on? We've just converted liter into millimeter cubed. Okay.
Yes, sir.
This is what, 400 over pi into 150 square. Now 100 cubed comes into the picture. So it's Newton. And so what? So everything cannot cancel out.
So we have upon area square, not just area.
Oh, we have area squared. Okay, so it's pi 150 squared, and this is millimeter square. Okay. So
Yes, sir.
so this is how many so this is 5 and this is 3. So you get over millimeter square. Okay. So what is a kilopascal? It is 10 to the power 3 Newton per meter square, right?
Yes, sir.
Okay, so what do we get? So this is 400 times 100 cubed over pi into 150 square whole square. And now we must convert this into this form. So Newton, so 1 millimeter is 10 to the power minus 3 meter. So we get 10 to the power 3 squared. So we get meter square. So I'll just write this over here. And we multiply by 10 to the power 3 on both denominator and denominator. So this is our kilopascal. And so finally we get 400 into 100 cubed over pi into 150 squared whole squared into 100 10 to the power 3. So 10 to the power 3 cancels out with one of this. So we get 10 to the power minus 3. And this is 100 cubed. So this is what? 4 10 to the power 2 into 10 to the power 2 to the power 3, 6 divided by pi into 150 square whole square. And this 10 to the power minus 3 goes upstairs and becomes 10 to the power 3. So I have a calculator handy with me. So what do we get? 400 into 1e6 into 1e3 divided by pi times 150 squared whole squared. I am getting 80.056.
Yes, sir. I'm also agreeing.
So when we squared the area, I think we forgot to square the 4 also.
There's a
The area is pi d square by 4.
yeah. So there's a 4 into missing everywhere. So there will be a into 4 over here as well, right?
Yes, sir.
Okay, so 320 point what? 320.22.
2.
Sir, in exams we have partial marking.
Huh?
Sir, in exams we have partial marking.
Not really. I mean, of course there will be, but don't harbor on that. I mean, so with the help of this, now we can simply put V in liters over here. So what is the final pressure? So let's just verify. So when V equal to 1.5, P equal to 120.9. Okay, this is correct. Meaning When we put P2 and V2, they'll check out. So now P3 is 200, so I will write 200. So this is P3. 200 equal to 120.9 plus 320.22 V minus 1.5. So what is it? So what do we get? 200 minus 120.9 divided by 320.22 plus 1.5. Yeah. 1.747. So V3 comes out to be 1.747 liter. Okay, so this is 1.747 liter. That's fine. We know what the total mass is. Total mass is going to be the same. So let's go to ES, and I will write over here P3 is equal to 200. V3 is equal to 1.747 into 0.001. We have converted liter into meter cubed. So now V3, so the specific volume at point 3 will be equal to the total volume, that is V3 divided by the total mass. Okay, so let's run this. So the specific volume at point 2 is 2.107. So you can write over here 2.107 meter cube per kg. So now, what is the question? What is the cylinder temperature when the pressure reaches 200 kilopascal? Okay, so I simply need to fetch T3. T3 equal to temperature, steam, P equal to T3, and V equal to V3. So temperature is 640.5 degrees Celsius. Okay, so this was the temperature over here was 105 degrees Celsius. Now, what is the temperature at point 2? I don't know what the temperature of is at point 2. I will simply write over here T1 equal to 105. Okay, T2. Why do I want to find out what T2 is? Because then, I mean, I can plot them on the PV diagram and see whether everything makes sense or not. Temperature, steam, V equal to V2, P equal to P2. So the temperature at point 2 comes out to be 203.6 degrees Celsius. What does that mean? 203 degrees Celsius at the same pressure, 120.9 kilopascal. When the temperature at point 2 is 203.6, it is obviously larger than the saturation temperature. 105 degrees Celsius is also the saturation temperature, which corresponds to 120.9 kilopascal. And therefore, state point 2 is a superheated vapor region. Is that clear?
Yes, sir.
203.6. Okay, so in reality, I mean, this is the vapor dome, saturated dome. And this is how the process will look like. Well, you don't need to take my word. Let's go and plot. Property plot. We'll go to steam. We'll go to PV diagram. Don't include all this. We do want. I don't want anything. In fact, let's just put some isotherms. So 120 isotherm we will put. We will put an isotherm of 203.6, and we'll also put an isotherm of 640.5. Let's do it.
So T1 is 105, no? Isotherm.
Uh-huh.
Like first isotherm, we should put 105. No?
What did I put? 120.
120.
Come on. Plot, property plot, steam. What was it? 105. Then 203.6. Then 640.5. Okay. Okay. So these are the three isotherms that we know. Now we will go to plot. We will go to overlay plot. Then we will on the y-axis, on the x-axis we have the specific volume. On the y-axis we have the pressure, and we will plot it with a blue line. Okay. This is the entire process. Okay. It's going from here to this isotherm and then linear curve to the other point. Okay.
Yes, sir.
So over here you can get the different properties below as well. I mean, anyway. So this is how you do it. Now the challenging part, not the challenging part, but when you want to do this all using table, it's not difficult. I'm not saying it's just a bit tedious. Okay, it is just a bit tedious. But the chain of logic will remain exactly the same. Okay, the, everything else will remain exactly the same. As per the book, the answer is 641 degrees Celsius approximately. And what did we obtain? 640.5. So, I mean, their answer is approximate, our answer is exact. Okay, guys. Hello.
Yes, sir.
Yes, sir.
Yes, sir.
So these problems will look a bit menacing. Okay, the problems will look a bit menacing. Don't worry about that. As long as you go step by step, nothing can go wrong. Okay. 8.1. You just need to take it easy. I mean, no need to get flustered about anything. 8.2. 8.3. This calculation might be a bit off-putting to someone, but come on, I mean, you're going to be engineers. I mean, you're going to be people who are going to do all sorts of deep learning, shallow learning, machine learning, horse learning, whatever. So this is the least you can do. Of course, without making an error. Can a computer actually just read the problem and solve these questions? Like, can it create the schematic, figure out the state points? Who knows? It should be possible, no?
Sir, but if we simplify the question, it can do, I guess.
No, it should just look at the schematic and do it. Like, okay. Well, then you won't have a teacher in that case. Machine would be doing problems. You and I would both be sitting and looking at the computer doing some problems.
So, but computer can't make us understand the concept behind it.
Who knows? Who knows? Maybe one day they will, like the Terminator movie, when they become Sentinel and then they start doing their own stuff. So there's a small concept that I want to just wrap up in this 15 minutes that's remaining. That is ideal gas. That's the idea of ideal gas. So problems, let me save this file. Chapter 03 Advanced Problems. They're not really advanced, but yeah, Contact calls them advanced. I'll create a new file. Create a new file. File new. So now we will look into a bit of ideal gas. So in the PV diagram and all, we've looked at how when real fluids behave, but we have not yet seen what the deal is with the ideal gases. And so ideal gas, as you can imagine, so let me first draw PV diagram. This is the TV diagram. And we know that in the TV diagram, these are going to be the isobars. These are going to be the isobars. And actually the slope of these lines is actually more drastic than what I am drawing since that day. The slope of these lines is rather like this. It's a bit drastic. So we know that this is saturated dome, liquid and vapor coexist, and this entire region is the superheated vapor. Okay, so now in the superheated vapor region, when the temperature is very high, so let's see, when the temperature is high and the pressure is low, then we can treat the vapor as an ideal gas. Meaning, like this spot over here, I mean, there is no, I mean, I've just drawn the boundary arbitrarily, but in this spot over here, this is like the edge where now you need to start treating it as a real gas. Over here, you have some error, but this region can be modeled as an ideal gas. Okay, so now let us quickly review the equations because every one of you has been doing this since ages. So experimentally, I mean, the thing is, experimentally, it is known that low density gases, low density gases meaning the molecules are behaving independently of each other to a very large extent. There's no crowding, there's no huge number of collisions or energy dissipation. So for low density gases, we know that PV is equal to N R bar T, where R bar is the universal gas constant. And the universal gas constant is 8.3145 kilonewton meter per kilomole Kelvin, or essentially it is kilojoule per kilomole Kelvin. And the temperature over here is absolute temperature. It's not in degrees Celsius, it is absolute. So this mistake many people will do, but you must remember that it's the absolute, and the temperature in Kelvin is temperature in degrees Celsius plus 273.15. Okay. Whenever you have division, multiplication of only T going on, you must use the absolute values. I mean, we will come to the actual justification when we deal with the temperature scale in the topic of entropy. Okay, so the basis is quite involved, but okay, for now, this is enough information for you. So now what we can do with this is, we can write this down as PV, or we can write this as PV bar equal to R bar T, where V bar is the specific volume on molar basis. It is the specific volume on a molar basis. Alternately, you have PV is equal to, so N, number of moles, is the mass of the gas divided by the molecular weight. Okay, so this becomes M times R times T, where R is defined as the gas specific universal gas constant. So it is universal gas constant over the molecular weight of the gas. Okay, so this is gas specific. I mean, it's gas specific, but it's the universal gas constant. So then we can write PV is equal to RT, where V is now the specific volume. This we know by definition. Specific volume. This is the specific volume on mole basis. Okay. Any doubt so far? I mean, there should be absolutely no doubt in this. Anyone?
So,
Yeah.
so in our diagram, TV, I didn't get that the red line. Like what ideal gas is on right hand side and left hand side.
No, it could be any. I mean, we have drawn it for steam, say for example.
So like on the left hand side of that red line, the
We
steam is
must treat
behaving as
superheated vapor as real gas, basically.
real gas, and right side
It
is ideal
starts,
gas.
so we can start approximating as this equation.
Okay, sir. Okay.
In order to fetch the properties, you can now use these equations when you are in the ideal gas region. And the ideal gas region is high temperature, low pressure, and that naturally corresponds to low density gas.
Yes, sir. Got it.
So now, to elaborate further on your question, we will define what is known as the compressibility factor, and this is something which you might have done as well. Compressibility factor. Okay, so compressibility factor is defined as the deviation from the ideal gas behavior, and it is defined as PV over RT. When Z equal to 1, then we say that the gas is very close to being an ideal gas. So let me just fetch a diagram to elucidate this point. Just a moment. Just grab hold of a diagram. So on the y-axis, we have the compressibility Z, and on the x-axis, we have the pressure, and different isotherms are also plotted. And this is for nitrogen. So this is for nitrogen. Okay. So nitrogen under these conditions. So for 200 Kelvin isotherm, for pressures between 1 bar to 4 bar, and then so basically you want to remain as close to this region as possible, is what I'm trying to say. You like to stay in this region. This deviation, and this deviation, you cannot use ideal gas equation, you must use a real gas property. Okay, so here in this band, whatever temperature pressure range you have, you can use ideal gas. Obviously here you have liquid nitrogen, so you must use real gas. Here you must use real, here also you must real. Okay, and that is quantified by means of the compressibility factor. Is that clear?
So the
Yes.
volume in compressibility factor is the normal volume or specific volume?
This one is the specific volume. It's I mean, you don't need to remember it that way. It's basically just this divided by this.
Yes, sir.
Okay, so all good. This was just a small point, so you will have some questions pertaining to this as well, but they will be very simple questions. All right. So let's call it a day. And
The points at which these curves are cutting compressibility factor Z is equals to 1, they are Boile's temperature, no?
they are what temperature?
So the points at which Z is going equal to 1. So what those points are called? There's a special name for it, no?
Oh, I don't know. There could be a special name for those. Possible. I would imagine there would be a special name for the minima in the compressibility that happens. There's a local minima, you see. When you're sitting on an isotherm and you're increasing the pressure, there is a point where the compressibility is minimum. Okay, so I would imagine that there is a special point for that. But I mean, it doesn't matter. You can call it anything you want. You can call it what's your name? Adarsh. You can call it Adarsh point. Okay. You know, like the Adarsh Balak. You can call it Adarsh point. ये वाला बिंदु बहुत आदर्श है. There you go. Yeah, it makes more sense because there it becomes z equal to 1. So it is really ideal gas. So ideal is Adarsh, right? Adarsh means ideal.
Yes, sir.
यहाँ बल्लेबाजी करने के आदर्श क्या पिच है यार मोट के नहीं. Okay then. So let's wrap up this. We have finished chapter 3. I'm not gonna do chapter 3 anymore. Now it is the onus is on you to solve as many problems as possible from chapter 3. Look into some of just a small reading task I'm giving to everyone. Just look at what the reduced temperature, reduced pressure, and all these things are. You've done this in your JEE, I know this. Okay, so it's Sontag section, or rather page number 66. Page number 66, you have those points. So solve as many questions as possible. Only then you will get the confidence. Solve the questions that I mentioned today as well. Page 66. So next week we will try to wrap up chapter 4 at least. Okay. So I guess I'll see you on some of you on no all of you on Tuesday. I'll see all of you on Tuesday on Mechatronics Lab. And if you're not able to make it to the lab, we will see each other on Wednesday.
So,
Yes.
so for the mechatronics lab, so can you